that you can hear me. I've just clicked the record button, so the session is being recorded. So as soon as you confirm that you can hear me, then we'll get started. Okay, perfect. Thanks, Ms. Opperman. Let's think about some admin goodies. I've loaded solutions for you for tutorial 2 and tutorial 3. I am setting up the worksheet for tutorial 4 for this week, and I will post it probably by 12 o'clock this afternoon or so. Webwork 2 is underway, as you would have seen. You can expect to have webwork exercise sets for the next few weeks because of the restriction by the faculty, we lost out on 2 weeks, I think. So we need to make sure that we catch up. So there will probably be another one next week. And then we need to start talking about the semester test. So if I remember correctly, your semester test 1 is on 27 March. And so we are moving closer to that date. I think we will cut off at 11.6 for semester test 1. And you can expect the same kind of format that you had for the 1B semester tests and exams. In other words, roughly half of the marks will be multiple choice in Blackboard, and the other half will be questions where you have to write an answer and load a PDF into Blackboard afterwards. So all of you have had enough practice with that. You should be able to do it without any hiccups. Okay, so that's all I can think of that needs to be said. I know I still owe a few students, 2 or 3 people. I've seen solutions that they want checked. I still haven't had time to look at them. I will look at them in the next day or 2 and send you some feedback on that. Okay, I'm going to share my screen and we'll get started. So this week, we have 2 sections that we are doing. So we will cover one section in this lecture and another section in the Thursday lecture. What I'm going to do, so today is definitely the last day that I will be able to offer this lecture at this time. And the reason I'm still able to do it this week is because the first year program was postponed by a week. So the faculty has decided to give the first years another week to register, which means effectively that this particular lecture slot, I don't need to lecture them for today, but next week we are starting with that. I'm starting with that module. So I will definitely be recording the lecture beforehand and posting it. So to try and make sure that we've got a seamless move over to the new system, I'm going to record the lecture for Thursday and post it sometime on Thursday, hopefully Thursday morning already, so that you can download it and have a look and make sure that everything's okay. Okay, so the 2 sections that we cover in this week are 11.4, and that one's called the comparison tests, and then 11.5. Both sections are quite short. So let's see how we go. We should be able to finish 11.4 in this lecture. Right, now, in this section, 11.4, we will have 2 tests. And with these tests, the basic idea is to compare a given series with another series. And for the second series, we know that that second series is either convergent or divergent. So if you look at the detail as we go through it, it should remind you of the comparison tests that we did for improper integrals in section 7.8 in the Maths 1A module, right? It's very similar. Yeah. Okay, so let's introduce the concept by looking at a particular example of a series and see how we can determine whether the series converges or diverges. That process of looking at this particular series, the sum from 1 to infinity of 1 divided by 2 to the n plus 1, is going to lead us to the general rule. Okay, so here's what we want to do. Before I tell you what we want to do, a lot of our arguments will be supported by inequalities. And so I thought it's probably a good idea to remind you of the 5 rules that we discussed in the 1A module that help us solve inequalities and work with inequalities in general. And so these rules come from Appendix A in Stewart's textbook, and here's what they look like. So if A, B, and C are real numbers, then it is the case that if A is less than B, then A plus C is less than B plus C. If A is less than B and C is less than D, then A plus C is less than B plus D. If A is less than B and C is a positive number, B is greater than 0, then A times C is less than B times C. If A is less than B and C is a negative number, then AC is greater than BC. So that's the one where the direction of the inequality changes. A is less than B, but AC is greater than BC. And then the last one says if A is less than B and they are both positive numbers, then if I take their reciprocal, I also flip the inequality. I change the inequality sign. So A is less than B leads us to 1 divided by A is greater than 1 divided by B. And so as we go through this section and the rest of the module, we will constantly need to use these rules for inequalities in supporting our arguments. Okay, so here's what we want to do. We want to show that the sum from 1 to infinity of 1 divided by 2 to the n plus 1 is a convergent series. Now, what we're going to do is we're going to use an existing series, the sum from 1 to infinity of 1 divided by 2 to the n, which we know is a convergent series. We're going to use this in our argument. And now we start building up our argument. So we know that if n is a natural number, then 2 to the n is less than 2 to the n plus 1. And if you go back and look at the rules that I showed you on the previous slide, you will see that we can support this argument, this statement, or this implication. We can support it by rule 1 above. And using rule 5, we have that 1 divided by 2 to the n plus 1 must be less than 1 divided by 2 to the n. And of course here, to use rule 5, we also need to know that both of these 2 to the n and 2 to the n plus 1, they must both also be positive. But that's also the case, right? If n is a natural number, then 2 to the n is a positive number. So now we reason as follows. We say we know that the series, the sum of 1 divided by 2 to the n is convergent, and we know that it has sum 1. And this, together with the fact together with star, the fact that 1 divided by 2 to the n plus 1 is always less than 1 divided by 2 to the n, means that if we look at the sequence of partial sums of the series that we are interested in, that sequence of partial sums must be bounded above by 1. It's got an upper bound. Also, we know that since all the individual terms, since each nth term is a positive number, the sequence itself must be increasing. And so we've got an increasing sequence, which is bounded above, and we've got that tool, the monotonic sequence theorem, that says under those conditions, this series must converge. And so we've proved that 1 divided by 2 to the n plus 1, the sum from 1 to infinity, must be convergent. And so I said to you that this is going to illustrate a way in which we reason about this, and it leads us to this test which we call the comparison test. And this test again has two components to it. So suppose that we know that the sum of an and the sum of bn are series with positive terms. If the series bn, the sum of bn, is convergent, and each an is less than or equal to each bn for every n, then the sum of the an must also be convergent. Alternatively, if the sum of the bn is divergent, the series, the sum bn from 1 to infinity is divergent. Now notice now the an must be greater than or equal to the bn for all n. Then we know that the sum of the an must also be divergent. So it's going to be important that we get the directions correct. In the first case, we need to know that the series with which we compare, the comparison series, we need to know that the bn is convergent and that the an is less than or equal to bn. Then we can conclude that the series an is convergent. In the second part of the test, we need to know, firstly, that the sum of bn is divergent, and that the an is larger than or equal to the bn for all n. Under those conditions, we know that the sum of the an must also be divergent. Okay, and of course, like everything else we do in the module, we will look at the proof. And to prove this, we're going to give ourselves some partial sums to work with. So we let Sn, the partial sum up to n terms, be the partial sum for the series Ai. We let Tn be the partial sum for the series Bi. And we let T be equal to the sum for the comparison series. T is equal to the sum from 1 to infinity of Bn. Now, one of the conditions, one of the prerequisites, one of the hypotheses in the comparison test is that both of these series have positive terms. In other words, An is greater than or equal to 0, is greater than 0 actually, and Bn is greater than 0 for all n. Then they're called positive terms. Now, since both of them are positive terms, these partial sums, the sequence of partial sums, must be increasing. So if you think about it, Sn plus 1 is Sn plus An plus 1. So if the An plus 1 is always going to be a positive number, then it's clear that the Sn plus 1 must be larger than Sn because of what's on the screen. Also, we know that the Tn has a limit t. It approaches t as n goes to infinity. And so the Tn is less than or equal to t. Now notice in this case we've assumed, for one, we've assumed that the sum of Bn is convergent. So that T that we're talking about is a real number. It's not infinity. And so since for each I, AI must be less than Bi. That's what we've assumed as well. We have that the nth partial sum, Sn, must be less than the nth partial sum for the Bn. So Sn is less than or equal to Tn. And again, we've got that Sn must be less than or equal to T for all n. Now you know how we're going to reason. We're going to say, well, that means the sequence of partial sums Sn is increasing and it's bounded above by the T. And because of that, we can say, but we know that the monotone sequence theorem says that Sn must converge, which means in turn that the series An converges. And we've proved part one. What about part two? Remember now, for part two, we are assuming, part two says, if the sum Bn is divergent and the An is greater than or equal to the Bn for all n, then the sum of An is also divergent. Let's prove that. Now, if the sum of Bn is divergent, then it means Tn grows larger and larger as n grows larger. Right? Tn goes to infinity, we say, since the sequence of partial sums is increasing. But now, the Ai is greater than or equal to Bi. So the sum up to n terms for Ai must be larger than or equal to the sum up to n terms for Bi, which means the Sn must also go to infinity. Okay? And hence we've shown that the sum of An diverges. So something you would have spotted immediately, but we need to talk about a little bit, is when we use this test, of course we must have we have the series for which we are interested in determining whether it's convergent or divergent. In this case, it's the An. And then we've got the second series, the series which we know is either convergent or divergent. Now, in the rest of the module, whenever we use this comparison test, we will use for the sum of Bn usually one of two types of series. The first one is a P series. And we know that for a P series, what does it look like? Well, the P series, a P series has general expression 1 divided by n to the P. And that converges if P is greater than 1, and it diverges if P is less than or equal to 1. The second standard series that we will be able to use when we use the comparison test is a geometric series. And here you'll remember the general expression for geometric series is the sum of a r to the n minus 1. And it converges if the absolute value of r is less than 1. And it diverges if the absolute value of r is greater than or equal to 1. Okay, let's look at some examples. So in developing these arguments in the examples, I didn't explicitly at all steps mention the rules that I mentioned in the beginning of this lecture, but they are there. So as you go through them, see if you can identify which ones we are using. So here, for example, we start by saying, if n is a natural number, then we know that 2n squared plus 4n plus 3 must be larger than 2n squared. So if you think about this, you should be able to get this from rule 1 again. All right? And now that rule 5 allows us to take the reciprocals. So there we changing, in the next line, we're changing the direction of the inequality. 1 divided by 2n squared plus 4n plus 3 must be less than 1 divided by 2n squared. And now I can multiply both sides by 5. And now I'm using rule 3, right? Right, because the 5 is a positive number. It's a positive real number. Okay. So now next, we consider the fact that we look at 5 divided by 2n squared on the right-hand side. And we know that if we take the sum from 1 to infinity of that expression, that we can factor out the 5 over 2, and we get 5 over 2 times the sum from 1 to infinity of 1 divided by n squared. And now that looks like a convergent series, right? It's convergent because it's going to be a p series with p equals to 2. And so the sum from 1 to infinity of 1 over 2 to the n is convergent. And by one of our theorems in section 11.2, the one where you can multiply the limit of a convergent series by a constant, we know that 5 divided by 2 times the sum from 1 to infinity of 1 over 2 to the n is convergent as well. Okay? And so by part 2 of the comparison theorem, we conclude, I think that should say part 1 actually. I think there's a mistake there. Let me double check. Yeah, that should say part 1 of the comparison theorem. Okay, I'll fix that up. I'll fix it in the notes. And by the way, I've already posted a version of the notes for this lecture. I'll fix that and repost it a little bit later. So now let's look at a little bit more detail in the conditions. Now, one of the conditions in the comparison theorem says either an must be less than or equal to bn for all n, or an must be larger than bn for all n. Well, if you think about it carefully, we don't actually need it to hold for all n. As long as it holds from some stage, some capital N, that capital N might be 1,000 or 1,000,000, doesn't matter. As long as for all of the n's larger than that capital N, it is the case that an is less than bn, or an is larger than bn. And this again comes from the fact that the convergence or divergence of a series is not affected by a finite number of terms. Remember what finiteness means. So a set with 1 billion elements is a large set, relatively speaking, but it's still a finite set. So any real number, any natural number, represents a finite set. Okay? Infinity is much larger than that. Another example. Test the series, the sum from 1 to infinity of ln k divided by k for convergence or divergence. So, previously, we looked at the same example, and we used the integral test to test the series. But we can also test it by comparing it with the harmonic series. So let's see how we do that. Now, we notice that ln of k is greater than 1 when k is greater than or equal to 3. See now there, our capital N in the previous note becomes 3. And so, ln of k divided by k is larger than 1 divided by k for k larger than or equal to 3. And now we know, look at what we have on the right-hand side, 1 over k. That should remind you of the harmonic series. 1 over k, the sum from 1 to infinity, is the harmonic series. It's p series with p equal to 1, and we know that the harmonic series diverges. And so the series that we are going to generate by using the kth term on the left, ln k divided by k, if we sum that from 1 to infinity, must also diverge by the comparison test. Okay? Okay, the second note. Now, the terms of the series being tested must be smaller than those of a convergent series or larger than those of a divergent series. So go have a look at the test again, the conditions. And in fact, it's quite intuitive, right? So, I mean, it's not very deep. You should be able to see immediately which direction it works and how the inequalities should go. Sorry about that. Now, if the terms are larger than the terms of a convergent series, now look at what we're doing now. If the terms are larger than the terms of a convergent series or smaller than the terms of a divergent series, then in fact, we know nothing. We are not able to conclude anything. And we can't use the comparison test. For example, if you look at the following setup, we want to compare the series from 1 to infinity of 1 divided by 2 to the n minus 1. And we use the inequality, the fact that 1 divided by 2 to the n minus 1 is larger than 1 divided by 2 to the n. And you can now go back to a starting point and develop an argument and show that this is the case. Now, the point is, with this inequality, we can't use the comparison test because the series represented, the term of the series represented on the right-hand side is convergent. And the thing on the left-hand side, the 1 divided by 2 to the n minus 1, is larger than that. So that means the condition, one of the conditions for allowing us to use the comparison theorem is not satisfied. Okay, so go look carefully, make sure you know how to use this theorem, this test properly. So this is useless as far as the comparison test is concerned because the sum of bn, the sum from 1 over 2 to the n, is convergent and an is larger than bn. Now, we do have the feeling that it looks very similar to a convergent series and we expect it to be convergent. And so we can use a different test. The next test we do is called the limit comparison test. And here's what it looks like. Suppose that the sum of an and the sum of bn are series with positive terms. If it's the case that the limit as n goes to infinity of an divided by bn is equal to c, where c is a finite number, in other words, c is not infinity, and where c is positive, then either both series converge or both series diverge. You can't have one of them converging and the other one doesn't, under the given conditions of the theorem, or vice versa. You can't have one diverging and the other one converging. They either both converge or both diverge. Let's see why that's the case. Now, we assume, before we start the proof, we assume that everything in the hypotheses hold. In other words, we don't explicitly say it, but we suppose that an, the sum of an and the sum of bn are series with positive terms. And we also assume that the limit as n goes to infinity of an divided by bn is c, and that c is a finite number and greater than 0. Now we start our argument. So this c is a finite number. And since it's a finite number and it's positive, I can pick two numbers, a lowercase m and an uppercase m, which are larger and smaller, or smaller and larger respectively than c. Okay, now Having done so, I reason as follows. Now, the limit as n goes to infinity of a divided by bn is c. Now, what does that mean? It means that this expression an divided by bn, that number, if I calculate it for larger and larger values of n, then an divided by bn gets closer and closer to c. And because I can do that, at some stage, I can be in between m, lowercase m, and uppercase m. So I will be able to find an integer n such that this number an divided by bn will also be larger than m, lowercase m, and smaller than uppercase m. That's because of that limit. And now I can multiply both sides by bn and get, as long as lowercase n is larger than uppercase n, I have the fact that lowercase mbn is less than an is less than uppercase mbn. And so now we can reason as follows. If the sum of the bn converges, so does the sum of a constant times bn. Thus, an converges by part 1 of the comparison test. Okay. So there, notice that the sum of the bn converges, and the sum of the an must be less than or equal to that. And we've satisfied the conditions of the previous test, and hence we can conclude that the sum of the an converges. In a similar way, if the sum of the bn diverges, we use the other inequality, the one that says that the sum of the m, lowercase m bn is less than the sum of the inequality that the lowercase m bn is less than an. If the sum of the bn diverges, it's going to force the sum of the an to be divergent, because if the sum of the bn diverges, then the sum of lowercase m times bn also diverges. And so it forces the sum of the an to diverge as well. Okay, so now let's see how we can use the previous test to test the divergence or convergence of the series we mentioned earlier. The sum from 1 to infinity of 1 divided by 2 to the n minus 1. We're going to use the limit comparison test, and we're going to use an equal to 1 divided by 2 to the n minus 1. And the series that we're going to compare it with is going to be 1 over 2 to the n. Okay? And we know we can calculate the limit as n goes to infinity of an divided by bn. Is the limit as n goes to infinity. We've just replaced it now, each of the an and bn with its expressions. We simplify, we get the 2n, 2 to the n in the numerator, 2 to the n minus 1 in the denominator. And now we use our technique for calculating such limits. We divide above and below, or the numerator and denominator, by 2 to the n. When we do that, we get an answer that this limit is equal to 1. Now 1 is a positive number, and it's a real number, it's not infinity. And this means by our limit comparison test, we know that either both of these series, the sum of the an and the sum of the bn, either both of them converge or both of them diverge. But we know that the sum of the bn converges because it's a p series. Because it's a harmonic series, right? And so, not harmonic series, it's a geometric series. And because it converges the sum of the bn, it means the sum of the an must converge as well. Okay? So this limit exists, and the sum of 1 over 2 to the n is a convergent geometric series. The given series converges by the limit comparison test. Example 4. It's a slightly more complicated expression. Determine whether the series, the sum from 1 to infinity of 2n squared plus 3n divided by the square root of 5 plus 5n to the 5 converges or diverges. Now, this expression looks quite complicated. And so we look at what's going to have the biggest influence on how large this expression becomes. We ignore the sum for now. So look only at 2 times n squared plus 3n, and the denominator, the square root, underneath the square root sign. If you think about it, the size of this expression is always going to be determined by, in the numerator, the 2 times n squared, and in the denominator, the n to the 5. But the n to the 5, we take the square root of that. And so in the denominator, it's n to the 5 divided by 2, right? And so what this suggests to us is the an is left unchanged. Remember, we need to construct a bn, which is going to be a term in the series that we use for comparison. So for the bn, we simplify the bn by saying, let's look at 2n squared divided by 5 to the n to the 5 divided by 2. And if we simplify that, we get 2 divided by the square root of n. And now we plug this into our limit comparison test. We say limit as n goes to infinity of a divided by bn is the limit as n goes to infinity of 2n squared plus 3n divided by the square root of 5 plus n to the 5 times the bn. We multiply that in, we simplify, and now we divide again, numerator and denominator, by the highest power occurring in the denominator. When we do that, we get the limit as n goes to infinity of 2 divided by 3 divided by n plus 3 divided by n divided by 2 square root, so on, and that becomes 1. And what do we know now? Well, now we can reason like this. The bn that we constructed is divergent because it's a p-series where p is less than 1. And because of that, we know that the other series, the one that we compared it with, must also be divergent. Okay. Now, let's spend a minute or so looking at what we did. Although we did it in a little bit of detail, you are going to have to decide how to simplify an expression like that, right? How to come up with a bn. And so let's just look a little bit at how we did that. So when we find such a testing series, it often works to construct our bn by keeping only the highest powers. So that's, if you think about it, that's really what we did there. We kept the terms with the highest powers. So there we kept in the numerator the 2n squared, because that's the term in the numerator that had the highest power. Similarly, we kept the highest power in the denominator. Okay? And that gave us n to the half. Let's see if we can get started with the next little bit. We'll talk for about a minute and then I'll stop and we'll have a look. Okay, so we've got another section here where we estimate the sum. So if we've used the comparison test to show that a series, the sum of an, converges by comparison with another series, the sum of bn, then we may be able to estimate the sum the sum of AN by comparing remainders again, as we did in the previous section. So if we consider the remainder, so here we've got the sum, the partial sum for the AN, the main series, the series which we need to determine whether it converges or diverges. And we call that remainder Rn again. For the comparison series, let's call it Tn. It's again the remainder of the sum up to n terms. Now, if An is always going to be less than or equal to Bn, then we must have that the remainder of the A series must be less than or equal to the remainder of the B series. So we must have Rn less than or equal to Tn. And if the series Bn is a P series, then we can estimate its remainder Tn, right? Like we did in the previous section. And in fact, if the sum of Bn is a geometric series, then that Tn is the sum of a geometric series, and we can actually calculate it exactly. Okay, we've run out of time. We only have one example left, so we'll do it in the beginning of the next lecture. So I'm going to stop, and I'm going to quickly have a look at whether there are any questions, okay? PTM Malobola says, so we can use the direct comparison test only when AN is less than BN, and limit comparison test when AN is greater than BN. So we can only use the direct comparison test only when, no, that's not quite correct. So the conditions are a little bit more complicated. So you can use the comparison test when the AN is less than or equal to the BN and the sum of the BN converges, right? You can use the direct comparison test also if the AN is larger than the BN and the sum of the BN diverges. So you have to have more conditions than the conditions that you specified there. Right, so I hope that answers your question. So this is what I meant. When you look at the conditions under which you can draw valid conclusions, you need to be careful that all the conditions are satisfied. For example, one of the conditions which we hardly mention is the fact that the AN and the BN, that all the terms in the two series or two sequences that are added must also be positive numbers. So a good exercise for you is to go and convince yourself that that is indeed a necessary condition. In other words, so you should be able to build an example that shows that if the AN has terms that are negative, that all the rest of the conditions can be satisfied, but the conclusion fails to hold true. Okay, so Mr. or Ms. Malobola, the answer is a little bit more complicated, but definitely send me an email if you're still not sure. Okay, we'll stop there. We've gone 2 minutes over time already. I'll post the recording that I post on Thursday will start from a little bit that I ended with, the last example from 11.4, and then the material from 11.5. Your next tutorial will be posted in the next few hours, and it will cover you until next week. Then we'll have 11.6 next week. We'll have 11.6 is a longer section, so it will be one section again for both lectures for the week, and then the week after that will be your semester test. Okay, thanks for coming. We'll speak again soon.